So this is kind of an interesting problem, um, discussing the stability of a pendulum system with damping. So it won't sway back and forth forever. It's being damped. This is like what a pendulum would behave like in the real world. So the general formula for the motion of a pendulum is going to be u double prime plus alpha u prime plus beta sine of u equals 0. That's the equation of motion for a pendulum. Where u is the angle that the pendulum starts from. So imagine if you had a pendulum here. That's a pendulum. That's what it looks like in its stable resting position. If you started the pendulum like here, this angle would be u. That's your initial angle. Um, and by the way, this term right here, the alpha u prime, that's the damping term. It's the damping term. So if you didn't have that, it wouldn't be damped. It would mathematically go on forever. So we want to discuss the stability of this. Namely, we want to show that u equals 0 is stable, but u equals pi is not stable. All right, we're gonna determine that here. Now we needed to define a couple of terms here. Uh, so actually, we're going to be proving that u equals 0 is asymptotically stable. Asymptotically stable right there. So what does this mean? It's important to know what we're doing first before we start doing it. Seems really obvious, but if you can't really solve a problem if you don't know what you're doing here. So this u equals 0 means the initial angle is 0 on this pendulum. So this is what that one looks like. Is that stable? Well, I mean, intuition tells us yes. Um, but I guess we should define what's asymptotically stable means. Asymptotically stable, um, astable, means that the system returns to its 0 position. Returns to 0 position. So in the case of our pendulum, it returns to this point right here with u equal to 0. Um, if you don't have stability, you don't have asymptotic stability, you just have regular stability, that just means that the system is bounded. System is bounded. That would be the case if we removed our damping term, the alpha u prime. That just means that the pendulum would, whatever angle you started at, it would just rock back and forth, back and forth, back and forth, back and forth. Um, but it would be bounded from below whatever this angle is that we started at. So that's what stability means. Not stable. Not stable. The system is unbounded. In the case of either of our two stable states, the astable or regular stable, the system is staying um, at an equilibrium position, or it's eventually converging to its equilibrium position, whether that be oscillation or the pure 0 stability, the pure 0 position there. So we're trying to prove that u equals pi is not stable. In other words, we want to show that this isn't stable, assuming that this is a massless, rigid bar right here holding this up, massless and rigid. massless and rigid there. So we want to assume that no outside forces are acting upon this pendulum, and this is going to stay put. Intuitively, this makes sense, I think. You know, of course, this is going to be stable right here, and of course, this isn't. It's not going to return to a stable state. It's just going to hang out there at the top position, not doing anything. Unstable, right? It's not returning to the zero position. Um, so let's do this mathematically here. We just kind of thought through it intuitively, but let's prove this mathematically. So let's do the first case. Let's do u equals 0. Show is astable. I'll put a little divider here so we can keep our thoughts organized. Um, so we just to reiterate here, this is our equation of motion for the pendulum. U double prime plus alpha u prime plus beta sine u equals 0. So let, there's a couple of theorems that I'm going to be using here to show this, but first we need to create a system of first order uh, differential equations here. So this is second order, but in order to apply some of the theorems we're going to be using, we need to convert it into a system of first order. So the way we do that is we let x1, I'll put a little let here, let x1 equal to u. All right, that means x1 prime is going to be u prime. Further, let x2 equal u prime, which means that x2 prime is going to be u double prime. And this is useful because what we can do now is we can make a system of first order equations. So we see that these x1 prime and x2 are the same. They're both u prime. So we can say that x1 prime equals x2. Further, we can say that um, that x2 prime, which is equal to u prime, is equal to minus alpha times minus alpha times x2 minus beta sine of x1. I'm just I subtracted these two terms from both sides right there to get this part right here, to get this part right here, and I just substituted in the x values were appropriate for u and u prime and so forth. So let's get rid of that. So this is our system. This is the same thing. It's just we can convert it to a matrix system and find its eigenvalues and say different things about its stability and so forth. So let's convert this into a system. So we see the exponent or the coefficient rather on the x1 on the first equation is 0. So our A matrix has 0 right here. I just realized I wrote an x squared there. That shouldn't be there. That should be an x subscript 2. So let me rewrite that as like that. X subscript 2. The coefficient on that is 1, so we have a 1 here. And in the second equation, we see that the coefficient on uh, on x2 is minus alpha there. Sorry, I had something stuck in my throat. Minus alpha right there. And this I didn't explain this, I guess, but this a is the Jacobian. I should have said that. Um, the Jacobian, by the way, is going to be the derivative with respect to each thing here. I guess I was saying that wrongly. So this is the derivative with respect to x1 the derivative with respect to x2, and then this is going to be the derivative with respect to x2 in the second equation. The derivative with respect to x1 in the second equation is going to be minus beta cosine of x1. You see that because the derivative sign is cosine there. So this is going to be minus beta x1, cosine of x1 rather, right there. Okay, so this is our Jacobian A. Another way to write this notationally, if you like that sort of thing, is the partial of f of 1 comma f2 over the partial of x1 comma x2. And we evaluate this at the point we're trying to reach here, which is 0, 0, 0, right? U being the zero solution. I guess this right here is more appropriate to say u equivalent to 0 because it could necessarily be a vector there. So we evaluate this Jacobian A at 0, 0. And we see that uh, this this Jacobian at 0, 0 is going to be this right here. It's going to be 0, 1 because there's nothing that depends on anything up there. But then in the bottom, it's going to be cosine of 0 is 1, so we have minus beta and minus alpha. Yeah. So there we go. Okay, so this is one of the theorems I'm going to be using here. So we can say that a system will be asymptotically stable if both of its eigenvalues are strictly of the Jacobian rather are strictly less than 0. So A stable if in this case lambda 1, lambda 2 are both strictly less than 0. If we had less than or equal to 0, we could say it was stable. They both have to be less than 0 there. Well, we have alphas and betas in here. Those are the constants on the parameters on the system of the pendulum. But it doesn't really matter what those are because we notice that an eigenvalue is going to be the sum of the eigenvalues are going to be the trace of the matrix. So that's a property of matrices that you would learn in like a linear algebra class. So the trace is the sum of the eigenvalues. The trace being the sum of the diagonal entries here, which is 0 minus alpha. So just alpha here, or minus alpha. That's the sum of those lambda values there. And another property is that the determinant is going to be the product. The determinant is going to be the product. So we see that the determinant of this matrix right here, this Jacobian, is going to be 0 times minus alpha plus beta, which is just beta. So we have beta is the product of these two eigenvalues, like that. Good. So we need to have these be strictly less than 0 for asymptotic stability. Oh, and by the way, that's because if we were to solve this with like a C constant thing, like let me do a little aside here. So you'd have C1 e to the lambda t dot 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 plus whatever else there is. Um, th this needs to converge for it to be asymptotically stable. It needs to converge to 0, which you see this happens if this lambda value is negative because it puts a negative exponent on this e. That means this whole thing goes to 0. If the lambda is positive, I guess there's the eigenvector attached there too. If the lambda is positive, it's going to increase without bounds. If it's 0, it's just going to converge to whatever this vector is. That's where that comes from. So notice here that the sum of two numbers is negative and their product is positive. Product is positive means they have to have the same sign, but they sum to be a negative number, so we see that they must both be negative, if that makes sense. Are negative. All right, and that makes sense. You know, they multiply to be a positive number, so they have to either be both positive or both negative, but then we see that they add to be a negative number, meaning they must both be negative. So they're both negative, therefore or equivalent, u equivalent to 0 is stable, asymptotically so, asymptotically stable, which we thought through intuitively makes perfect sense. You could actually prove this for any angle, except for the one we're about to prove. Any angle works, you know. They'll all eventually, with damping, they'll all eventually converge back down to this 0 position right here. And obviously, if it starts there, which we showed here, then it's going to be stable, asymptotically stable. All right, so now let's do the same thing, but for u equivalent to pi here. Let's see what happens. So in that case, the Jacobian is going to be the same. It's going to be 0, 1 minus beta cosine of x1 minus alpha. But instead, we're going to evaluate this at the pi 0 point, right at time 0. Pi is 0, so pi is the angle. T is 0 at time 0. So we evaluate this at pi comma 0. We see something interesting here. We see that 0, 1 up there, and then you plug in pi for x1 there. You see that this is the cosine of pi is -1, so this is a positive beta instead of a -1 like we had up there. Minus alpha is the same. And similarly, the determinant of this matrix will be the product of its eigenvalues. So lambda 1 and lambda 2, whatever they are, multiply to equal 0 times minus alpha is 0. So 0 minus beta. They multiply to equal minus beta, which means that for beta being positive or negative, that's one of our conditions on this formula, by the way. I didn't say that, but alpha and beta have to be positive numbers. For positive beta, that means one of these two eigenvalues is positive because the signs are different, so they multiply to be a negative number. Which, when you think about it, if we were to solve this system for its parameters, um, you have c1 e to the lambda 1 t times v1 plus c2 e to the lambda 2 t v2 plus whatever. Um, okay, so let's say lambda 1 is the -1. So that's fine. That means this thing converges to 0, asymptotically stable so far. But this lambda 2 would have to be positive since this other one was negative, which means this whole thing is going to increase without bounds to infinity, and this thing is not going to be stable. So that's it's interesting um, observation there. That means that the solution u equivalent to pi is not stable. It's not asymptotically stable. It's not regular type of stable. It's just not stable.